Okay, so now that we know what chemical bonds are, and we've talked about metallic bonds, so now we're going to get more into ionic bonds, and we're going to talk about how we name them and how they form, and then some of their properties. All right. So when we're naming them, it will sometimes get an ionic name. So let's first recall what cations are. Remember, these are positively charged. And so they'll usually be metals. Actually, almost always metals. All right. So these don't change their names. So, for example, if you have magnesium, the metal, or magnesium, the ion, you call them both magnesium. If the cation can have different charges, so some of the transition metals can have different charges to them, like we talked about last unit, then we use a Roman numeral after the name to show it. So for example, iron 2 plus, you would show as iron 2. That way you know it's different than iron 3 plus. Iron, and then with a 3 Roman numeral, right? So that shows the difference between the ions if it can have multiple ones. So like group 1 and 2 elements, or if it doesn't ever, or if there's only one charge that it can have, so like zinc and silver, then you don't need to do anything, you just say its name. But if an element can have 2 different charges, so the 2 that I want you to know in this class are iron 2 and iron 3, and then copper, right, can either be 1 or it can be copper 2. So those are the 2 that we'll be working with in the class. But, right, you should, from any name, you should be able to see what it is. All right, anions, and remember these are the negative charge, so these are usually going to be nonmetals. Their names do change. So, right, cations, their names don't change. Anions, their name does change. And so what we do is we drop the end of the name and then add "ide" to it. So, for example, nitrogen, we're going to drop the ogen, and it's going to be nitride when it's in its charged state, right? So that'd be when we're referring to N3 minus, all right? Or oxygen, we're going to drop all that, and it's going to become oxide. Sometimes, so you just need to practice with these, especially with the common ones. Sometimes, a lot of times it will just sound right or wrong, and that's a good way to figure it out. So let's, why don't you take a minute, try out these ions. Okay, so these are the answers you should have gotten. Li plus is lithium, Ca2 plus is calcium, Cu plus is copper 1, Fe3 plus is iron 3, F minus is fluoride, Cl minus is chloride, O2 minus is oxide, and S2 minus is sulfide. Okay, so now let's get into how ionic compounds form. So what happens is, right, when ionic compounds are when oppositely charged ions attract and stick together. And so what we see, right, so we have here sodium and chloride ions. They're going to come together to form sodium. Oops, I want my pen. Sodium chloride. All right. So what we want to always see is these. We'll usually see a metal ion with a non-metal ion coming together to form the ionic compound. And remember, we're showing just 1-to-1 right now, but but we will often find, or what it usually is really just a bunch of ions coming together. All right, so when ions bond, we want to have a ratio that produces a zero charge. So we're going to go through that. So we're going to start up here at the top. So if we have just magnesium 2 plus, or the magnesium ion, then that means our net charge is 2 plus right now. So then if we bring so now let's bring an anion in, and we'll bring in Cl minus. So what we get is 2 plus minus 1 to have still a plus 1 charge. So we don't have a zero charge yet. Now, if we bring in another chlorine, we have that plus 2 from the magnesium, a minus 1 from one chlorine, and a minus 1 from the other, and we have a zero charge. Now, let's say for some reason you're like, well, maybe one more. So we have the plus 2 from the magnesium, a minus 1 from each chlorine, and we have 3 of them, which means that we would have a negative 1 charge overall. So, right, these 3 means that the elements aren't stabilized because their charges aren't being balanced out. But here, the charges are being balanced out. So it's in a stable state, and so that's where it wants to be. So the way we would write that would be MgCl2. All right. So like I said, when these ionic bonds come together, or these ions come together to form a bond, it's not really just one of each element coming together, one of each ion coming together. It's really a bunch of them coming together. And when they do this, they form a crystal of trillions of atoms. But it's in a fixed ratio. So like we just talked about, where we want the ratio produced to be a zero net charge, these trillions of atoms are going to be structured in such a way that they're perfectly balanced each other's charges, and it's always going to be a specific ratio. So salt crystals are trillions of sodium and chloride ions, but they're always in a 1-to-1 ratio to each other because of the charges that these ions have. The crystals in the lattice structures are within a formula unit, and this is the simplest ratio of atoms that make up the lattice. Right, so that's what I was just talking about, where, yeah, we have these trillions of atoms of sodium and chloride ions, but they're always going to be 1-to-1. So its formula unit is always NaCl. Okay. So here are a few for you to practice with. So if you're just watching the video, then you can pause here and put these ions together. All right, so let's go over these. All right, so calcium and fluorine. So calcium has a 2 plus charge and fluorine has a 1 minus charge. So we're going to want 1 calcium with 2 fluorines to balance it out. And that's how we show it. All right, now sodium 1 plus and oxygen 2 minus. So we're going to have Na2O. Magnesium has a 2 plus and sulfur has a 2 minus, so their charges are equal to each other, so we just need 1 of each, Mgs. Aluminum has a 3 plus charge, chlorine has a 1 minus charge, so we're going to need 3 chlorine ions to balance it, so we'll have AlCl3. And lastly, aluminum 3 plus and oxygen 2 minus. So with this one, it's a little trickier, and you're going to have to think a little bit about what's a common denominator between them. And 6 is the common denominator between the two of them. So if we have 2 aluminums, then that's when we get the 6 plus charge. And if we have 3 oxygens, then we'd have a 6 minus charge. So we're going to have Al2O3. something you might have noticed. So, right, so one way you can do it, look at the charges, figure it out. Another thing you can do is notice how the charges basically dropped to the other side, and the numerical value is what went down, right? So here, if we had Ca2 plus and F minus, right, the 2 plus goes down, and the 1 that's for the fluorine minus goes down, and it becomes Ca with the 1 is just assumed, and then F2. Then you see that again with the sodium, right? Sodium has a 1 plus, oxygen has a 2 minus. So the 2 went to the sodium and the subscript. And it's not like it's getting the charge. We're just saying that there's 2 of them there to balance it out. So it's one way to figure it out is just drop the numbers down to the other side, and so that they're subscripts. The only one that doesn't really work with is if they're both 2s, because they're going to be equal to each other, so they balance each other out. Remember with these, we're always wanting the smallest whole number ratio available. So that's why putting Mg2S2 would be incorrect here. Okay, so let's talk about naming these. So now we know how they form, and their formula units. But we need a way to describe how we name them. So what you do, because they're in a set ratio, we don't have to state how many of each element are in the ratio in the name. When we name them, it's just the cation name, then the anion name. Right? So here, Al, that's aluminum, and O is oxide when it's in its charged form, so it's just aluminum oxide. All right, so pause here and give these a try. So first you're going to want to figure out what the formula unit is and then give them a name. Okay, so you should have found Ag and Cl minus is AgCl, and that is silver chloride. All right, Ag3 plus and F minus is Al3, and F minus is AlF3, which is aluminum fluoride. All right, Fe3 plus and N3 minus, remember iron, right, we're putting them together first. So that's all 1 to 1 then, so it's Fe N. So remember with iron, we want to state which type it is, so it's iron 3 nitride. All right, potassium in its charged form is K plus. And iodine in its charged form is I minus. So we'd have Ki, so that'd be potassium iodide. So iodine versus iodide. All right. Sodium, Na plus. Sulfur is S2 minus in its charged form. So it'd be Na2S. So sodium sulfide. Okay. All right. So now we know what how the ions form, how to name them, what their formula units are. Now we want to look at a special type of ion. We're going to talk about polyatomic ions. Poly means many. So right when people talk about sister wives and how they're polyamorous, right? That means they have multiple lovers, essentially. So not a Catholic idea, but it is something that exists in the world. So polyatomic, right? Many atoms in an ion. So polyatomic ions are ions made of several atoms bond together. And so it's like a clump of atoms that have a collective charge to them, and they act like a single ion. So even though there's going to be multiple atoms in the clump, they're acting like a unit together. Polyatomics have their own name. They generally end, the ones that we're going to be dealing with, they're going to end in 8, or they're going to have an unusual name. And we'll go into them more. So for example, we have sulfate. So that 8 tells you it's polyatomic, versus sulfide. That "ide" would be just S2 minus. The 8 tells us it's polyatomic. And what the ion is SO4 2 minus. So what this means is we have a sulfur atom bonded to 4 oxygen atoms. And overall, this structure has a 2 minus charge. So it's going to act like a unit. So just like if you have just the S2 minus, this SO4 2 minus, the 2 minus is what's going to dictate how it bonds and how the ionic compounds form with it, not the structure itself. So the 2 minus is what's going to dictate it more, not the SO4 part. All right, so these are all the common polyatomic ions that we're going to deal with. There's a lot more out there, but these are the ones that we felt are the most important for you to know. So you'll notice most of them will end in 8. So nitrate is NO3 minus. Sulfate is SO4 2 minus. Phosphate, PO4 3 minus. Carbonate, CO3 2 minus. Permanganate, MgO4 minate. Let me see, acetate is a special one here, a little bigger. Chlorate, ClO3 minus. Bromate, BrO3 minus. Chromate, CrO4 2 minus. Those are all the ones that end in 8. Then we have some special named ones. So we have ammonium, so that's NH4 plus. Hydroxide, so that one is a combination of hydrogen and oxygen, and it's OH minus. We have cyanide, so a combination of carbon and nitrogen, and it's CN minus. This one is a really deadly one. You don't tend to deal with it much. Okay, so when ionic bonds are forming for polyatomic ions, it's going to act like a single ion when they bond. So the only thing that matters is their charge. So when we were talking about sulfate, the SO4 part isn't what matters for the bonding. The 2 minus part is what matters with the bonding. So for example, if we have potassium and sulfide, then that would form K2S, right? So that should make sense. So if we have potassium and sulfate, what's going to happen is it's going to be K2SO4, right? The charge is what dictates how many of each ion you need. We never change the polyatomic part. We never change this ion itself. The charge is what's dictating how the bonding will happen. Okay, so let's give this a try. So you can pause here and give it a try, and then I'll go over the answers. Okay, so sodium is 1 plus and hydroxide is 1 minus, so they're going to form 1 to 1 to be NaOH. Magnesium and carbonate, these are, magnesium is 2 plus, carbonate is 2 minus, so they're also going to form 1 to 1 together. So you're going to have MgCO3. All right, potassium is 1 plus, phosphate, PO4 3 minus, so 3 minus charge. So we're going to have K3, because we want 3 positive charges to balance out the 3 minus charge of the phosphate. And it's going to be PO4, because we're just going to have one of those. And then potassium and acetate. Potassium has a 1 plus charge, acetate has a 1 minus charge. So it's going to be KCH3COO. All All right. So right, the charges are what matters. Okay. So now what happens if we need more than one polyatomic ion? So right, so here if we have ammonium, which is 1 plus, and oxide, which is 2 minus, we know we're going to need another ammonia, right? So, and we can't, if we write, look at the difference here. So if we say NH4, and then just put a 2, and then an O, that looks like 1 nitrogen and 42 hydrogen, right? So what we need to do is we need to put it in parentheses. So what we write is NH4, and we put parentheses around that, and we put a 2 there. So what that tells us is we have 2 ammonium ions, and then we put the oxygen at the end because we have 1 oxygen ion, right? So the parentheses really matters here. Let's look at some examples, right? So if we have calcium 2 plus and permanganate, right? Permanganate has a 1 minus, calcium has a 2 plus. So that means we're going to need 2 of the permanganates. So we're going to do Ca parentheses MnO4 and then a 2, right? Because if we don't put that parentheses around, so if you say CaMnO42 without the parentheses, right? That's saying we have 1 calcium, 1 manganese, and 42 oxygen, right? So that is not right. That's a completely different compound than when we have the parentheses around it. So parentheses, very important. All right, so pause here and give the rest of these a try, and then I'll go over them. Okay, so Mg2 plus, O minus, OH minus. So we'll have Mg, and we need 2 hydroxides, so we put parentheses around and give it a 2. Aluminum is 3 plus, carbonate is 2 minus, so that means that we're going to need 2 of the aluminums and 3 carbonates, so that's going to be Al2, parentheses, CO3, 2. Or sorry, 3. There, all right. Aluminum hydroxide will be Al, parentheses, OH, 3. Ammonium phosphate will be, parentheses, NH4, 3, PO4. Calcium and acetate, that'll be Ca, CH, 3, COO2. And then sodium and hydroxide, that'll just be NaOH. Because right, they're 1 to 1, so we don't need parentheses there. You only need parentheses if you have more than one of the polyatomics. Okay. Almost done with all this. So now for naming polyatomics, we do it in the same way. We say the cation name, and then the anion name. So, right, ionic compounds, they're forming these large crystal structures. So they have really strong bonds because they've totally exchanged their electrons. So this means that they're going to be found as solids typically because of that strong exchange of electrons. They're going to have high melting and boiling points, and they're non-volatile. So that means they don't go to gas easily. Right? So you could try to set fire to, don't you actually try it. With adult supervision, you could try to set fire to salt crystals, but nothing will happen. You really have to heat them up very high to get them to melt or boil or anything. But, so it takes a lot of energy to, if they're in their crystal structure, to try to, like, break them down in any way, or, like, you can't really burn them. But you can dissolve them in water. And we'll get into how that happens. But when they're dissolved in water, they become electrolytes. And they're called electrolytes because they will allow water to conduct electricity. So that's that flow of electrons that we see. And so when salts, or when ionic compounds get dissolved into water, they're going to allow electricity to conduct because they're able to move their electrons around with them. They carry those charges and push the charges around to allow electricity to flow. Oftentimes, these compounds are called salts because of this. Right, so a lot of times when we talk about salt, we're specifically talking about sodium chloride, but it can really refer to any salt. So like Epsom salt, right, is magnesium sulfate. Okay, so let's look at how this works. So water is, you can think of it as like the chaperone molecule. So when we put a ionic compound into water, the water is going to pull them apart and keep them apart. And this is because of, it has to do with charges and things like that, but the salts are able to separate from each other, or the ions are able to separate from each other when dissolved into water, because the water isn't going to actually let them bond. So, it's like the chaperone at the dance that comes by and tells you to leave room for Jesus, or leave some space for the Holy Spirit there, right? It's going to keep them separated from each other. And this is so, but once the water is gone, the ionic compounds will reform. So if you ever leave a glass of water just sitting out, right, you'll probably see some like stuff form on the bottom, and that's just salts from the tap water or what was ever left in it. And you do want salts in your water. It's really important. Actually, get into that right now. So salt is essential to life. I think I mentioned it when we talked about like sodium and potassium. It keeps our nervous system and heart functioning. Right? Our muscles wouldn't move unless we had salt in our bodies. Then that's a lot of biochem, though. And we get our salt through our diet. So, right, some of you might say, well, but I've been told that we need to limit the amount of salt in our diet. And that can be true for some people because too much salt in the diet can lead to high blood pressure, which potentially increases the risk of heart attack and stroke. And these are top killers in America. But this is usually a problem if you're eating a lot of processed foods. And this is because the processed foods are adding just a lot of sodium through other forms than just sodium chloride. So if you're eating foods in their natural state or minimally processed foods, adding salt isn't going to hurt you. In fact, it's going to be pretty important. Some people find that if they're eating a mostly like real food-based diet and they don't include salt in it, they start having like adrenal issues, which is like your adrenal glands above your kidneys. They might not produce enough hormones. They might develop really low blood pressure and have like fainting spells and stuff. So getting salt in your diet is important. But if you've been told by a doctor like that you need to limit it, it's probably more due to being on too much processed foods or eating too much processed foods versus just actual like pure salt issues. For athletes, getting salt is really important for proper muscle contraction. This is why, like, long-distance runners will carry salt on them. So when I did a half marathon, we, like, went to McDonald's and just, like, grabbed, like, handfuls of their salt packets and kept them in our little, like, belt. Because if you start getting a muscle cramp, you would just, like, down the salt packet and drink some water, and then your cramp would go away, because the lack of salts, because you're overusing your body when you're running a half marathon or marathon, you're losing electrolytes, and so your muscle isn't able to contract as well. And so by flooding your body with the salt, it's able to contract properly again. That's also why sports drinks were created. And if you ever find, like, you're just, like, downing water and water and water, and you're just not getting any you're just peeing it all out, you don't feel like you're hydrated at all, try adding a little bit of salt into your water, sometimes even a little bit of sugar. It'll help absorb the water better and help your body utilize it better. All right, so that is all about ionic compounds, some of their properties and why they're important for us.